I found the solution. Right, let's now look at trigonometric equations. The fact that we have looked at the inverse trigonometric functions put us in a good position to look at trigonometric equations and solve them. Because remember, I said it before, that inverse, the concept of an inverse is the one which makes possible to solve equations. All together? Okay, let's say solve. I'll take a simple equation here. It's like, let's start with sine t equals to, let's say, 0,5. I'm starting with a simple one, isn't it? Okay. Now, first of all, let's go back briefly to our circle. I think whilst we're on this circle, I'll say something here which you must get very, very clear. Notice, guys, that when we define sine or cosine, we say it is sine of an angle theta was equals to y over r, and r was the radius of a circle, isn't it? Okay. Now that immediately says the coordinate y is always equal to r multiplied by sine theta. In a similar way, x will be r cosine theta. But the most important thing which I want to emphasize here, this ratio does not depend on the radius. It depends on y. In other words, even if I take a circle here, which is bigger, I mentioned it the other day, but I didn't go as far as I want to go now. If I take a circle now which is bigger, and my angle is this one, when I define sine using the y from this point, or y from that point, or any other point on that arm, it will be the same ratio. Is that clear? Then, because I want things which are simpler, easy to manipulate, then for me, it's more comfortable to choose the radius 1. Then if I choose the radius 1, what happens? R here becomes 1, R there becomes 1. Then it says, always, on the unit circle, x is going to be cosine of theta. In other words, on the unit circle, I can just look at the coordinate x, I've got cosine. Is that clear? Are you getting that clear? Are you hearing what I'm saying? I said this ratio does not depend on r. It doesn't matter whether I take this circle or that circle or any other circle in between. The ratio will be the same for a given angle. Like the ratio is the value of the function, so it must be unique for a given angle. Is that clear? So then I'm saying, since it doesn't depend on r, I can then choose radius equals to 1. And that ratio which I calculate with the radius equal to 1 will be the same ratio for any other circle. Are you comfortable with that? Then I can choose my r to be equal to 1. Then this equality just becomes x equal to cos theta. Am I understood? Because it becomes 1 times cos theta. Then when I go to this one, it becomes y equals to sine theta. What is that telling you? It tells you that the values of cosine and sine are the coordinate x and the y on the unit circle. Do you hear that? So then if I got a unit circle and that thing is drawn to scale, instead of using it in a calculator, I can just look at the coordinates on the scale there, and I've got my cosine, I've got my sine. Isn't that beautiful? It's beautiful. For me, it's beautiful. Because I can actually deliver a calculator for trigonometric ratios to any place where if there's no electricity. What do? I just draw a unit circle to scale, very good scale, maybe to 2-3 decimal places. I draw it, I put it on a paper, I take the paper to Kazankulu, I take it to Kumbu. They've got a calculator for trigonometric ratios. They don't need a calculator. To me, that is beautiful. Are we together? Okay. But if you don't see the beauty, it's not a problem. It might be just that you don't have the eyes to see the beauty. And that's normal. Okay. Good. Now, coming to this equation. How are we going to solve this equation? I'm just going to put down the steps here, how we normally solve this equation. Now, you see, when I'm looking at this sign there, it says sign is positive. When I see sign positive, I know that in the definition, I'm using the y coordinate, which is positive, isn't it? So I can just glance at this and say, first coordinate, second coordinate, third coordinate, fourth coordinate, and just check where is y positive in these two, isn't it? So now what I can do, I can now say, let me take a reference angle and say sine theta 0 equals to 0, 5. Isn't it? What do I do? I'll be looking at this angle here in the first quadrant, isn't it? Then I get my calculator and say sine second function of sine t0 equals to sine second function of 0, 5. I'm applying the inverse function on both sides, isn't it? I know what's going to happen this side. What's going to happen? I'm going to get my t0 freed from that. Then I go to my calculator, I do this calculation. But that part I cannot explain. Depends on your calculator, how your calculator wants the sequencing of the keys there. Some calculators can just press second function sign, then enter 0, 5. Some calculators can enter 0, 5, then you enter second function sign. So, deals according to your calculator. That's right. What are you getting otherwise? I don't know. Come again? Come on? 5,6. Pi over 6. Okay? Pi over 6. Oh, sorry, said 6, ne? Pi over 6. Then what I'll talk about here? We're talking about this angle. I'm going to shade it. I'm going to talk about this angle. But we know that ratio is equal in the first quadrant. It is equal to what it is in the second quadrant. So what I'm going to do? I reflect this arm across and have another arm there in such a way that this angle is reflected there as the same angle. So this is T0 and this is also T0. But I'm not looking for this angle. I'm looking first for this one. Secondly, I'm looking for that one. All together. Here what I've used is just a reference angle. Now to get my solution, I'll then say, therefore, T is equal to pi over 6 for the angle which is in the first quadrant. Or T is equals to, now this one, whose terminal arm is this one, is going to be pi back T0, which means the pi minus T0. So it's going to be pi minus pi over 6. Then I've got my two angles there. In this case, I'll be talking about T, which is between 0 and 2 pi. Are we together, guys? Yeah. But remember, this is a trigonometric function, it's periodic. If I want to give a general solution for this equation, I will then say T equals to pi over 6 plus 2k pi. What am I saying there? I'm saying this ratio will repeat itself every 2 pi at these types of angles. On the other hand, I will say T is equals to, this is 6 pi over 6 minus 1 pi over 6. I'll get this 5 pi over 6 plus 2k pi, and I must remember there to say k is an integer. How together, guys? Okay. I've used here simple trigonometric equation, but what I want to emphasize is the use of the reference angle. Even if I had the arm of I had this ratio being negative. Let me discuss the case where this ratio is negative. Then you can see what I'm talking about. Up to now, is that clear, guys? Is it clear? Okay. So let me move to the next page now. You really want to copy everything there word for word when you're going to see that thing on a video clip. Okay. Right, right guys, let's see now. We are now put the equation sine equal to minus 0,5. Now, first of all, we know that sine is negative. The ratios negative where they're in the third quadrant and in the fourth quadrant. So I'm actually talking about an angle whose arm is somewhere there or there. All together. Now, which means I would like to look for this angle. On the other hand, I would like to look for that angle. Are we there? Okay. That is if I'm using the circle. Let me look at how would I look at it if I'm looking at the graph of the function sine. It will go up, down, up, 2 pi there. Notice that it's enough for me to find the angles between 0 and 2 pi. Then I can generate the rest of the solutions, isn't it? Using k, isn't it? Okay. Now, if I say this function is minus 0,5, let's say if this is minus 1 and that is 1, 0,5 is somewhere there, half, isn't it? Minus half. Now, if I say the sine value is minus half, I'm looking for the angle which corresponds to this angle in radians and also to that angle in radians. As you can see, this will be in the fourth quadrant, this will be in the third quadrant, isn't it? Remember, it's 1, 2, third quadrant, fourth quadrant, isn't it? Are we there, guys? So you see, I'm looking for 2 angles. But maybe this situation does not help me a lot, this one for the graph. This one will help me. How is this one going to help me if I'm using the reference angle? All what I need is to take this line and extend it straight across to what? To the first quadrant, is it? Then I now say this angle in the first quadrant is my T0, my reference angle. I will do that. Then immediately I will temporarily stop looking at this equation and look at the equation. Says sine t equals to 0,5 and say sine t0. T0 I'm marking what? The reference angle. Are we together? Then now I will solve this equation now and say, okay, notice one thing. If I take the angle which is vertically opposite to T0, I get another T0 here. Are we there? These two angles are vertical opposite, so this is T0. So the angle which is the first angle which I'm looking for is actually pi plus this T0. Are we together? So you see how I'm using my reference angle now. So once I've solved this angle, this trigonometric equation for the first quadrant using the reference angle, then I've got the one in the third quadrant. Then immediately I'll get the one in the fourth quadrant. How am I going to get the one in the fourth quadrant? It just consists in reflecting this one across the y-axis. T0 will be there. Or reflecting this one across the x-axis. T0 will be there. All together. So now the next angle which I'm looking for there is going to be 2 pi, which is at this level, isn't it? Then back T0, which will create as 2 pi minus T0. So what I've done there, I've just discussed the process. How do you go about it? Isn't it? I haven't solved it. Now let's come and solve this one. Now we're going to do here, apply the second function on both sides. This is going to be sine second function, bracket sine T0 equals to sine second function 0,5. Why are we taking advantage of this? We learned this, that if you compose a function and its inverse, it gives you back the argument which you're looking for, isn't it? So now I want to free T0 from sine so that it can stand as a substitute formula. The only thing we can call upon is the inverse function. Is that clear? Never, never forget that again. I said to you at the beginning, once we deal with the inverse, the concept of inverse function, then equations are easy to solve. We know exactly what we do. And because you can see, there's nothing moving here. You know the story of moving things and changing signs? There's nothing moving here. You just apply the function, the inverse function, then you get that. Then you get this t there. Then you go to a calculator. What was the value here? What was the value? Pi over 6. So now, from what you have said here, the angles we want is not pi over 6, the reference angle. The angles we want is this one, which is pi plus this T0, with that T0 being pi over 6. So now I can now write the solution. As you can see now, the solution you're going to get here, pi over 6 is not going to be involved except in addition or subtraction, is it? But in the previous example, because it was positive, pi over 6 was one of the solutions. Then you say pi plus pi over 6. But the pi is 6 pi over 6 plus 1 pi over 6, we get 7 pi over 6. Did you follow that? Did you follow that? Okay. Then or the solution is this one, which the arms is there. Then it becomes OT equals to 2 pi minus pi over 6. But 2 pi is 12 pi over 6. Isn't it? 12 pi over 6 minus pi over 6. Then you get our 11 pi over 6. Then we're done. Oh, 11 pi over 7. Said the blind man sitting at the corner of a round table. Right. That's right now. It's fine now, isn't it? Okay. So guys, I'm just discussing an approach to how you handle these ratios when they're negative, positive, whatever. Now I want to take you to take this experience to cosine, to sine, to to tan, and so on. Are we there? Okay. Now I think I'll pause there for a while. I think let's do this. Let's stop here as a basic building block to what we're going to do. Then in the next example, I want to take a kind of a more challenging example, because what's going to happen, we're not going to give you questions like this which come like ready to chew and deliver. No, we're just going to want to give you questions which are a bit more challenging, so that when you get to this stage, now you do this, but having done some other groundwork, you know. So I'm going to stop the slide there and say thank you for listening for that part. Let's see what comes in the next section.